Hello everyone, welcome to your next class. In this one we are going to be continuing our introduction into machine learning. Specifically what we're going to be doing is introducing you to some fundamental concepts around supervised learning. So remember, in this course we're going to be talking about two types of learning specifically, but I'm going to go through what each of them are and what each of them mean. So in this class you're going to learn some more important machine learning concepts, really specifically around what is a supervised machine learning model as opposed to a unsupervised machine learning model. I'm going to give you a description of what kinds of tasks they can fulfill and what they are used for generally within the industry. So I'm hoping at least rather, that by the end of this class, you will understand that there are three types of machine learning models and that they are involved in different types of problem solving, and we use them in different ways and have different ways of talking about them and different algorithms in order to get them done. So what are these three types of models? These three types of models are supervised learning, unsupervised learning, and reinforcement learning. Now, I've kind of put a question mark around reinforcement learning because there's still a bit of debate around whether or not reinforcement learning is its own type. For the most part, people do kind of have it as its own little thing because it's almost like a little bit of supervised and unsupervised going on. It's a kind of a hybrid model, and you'll see what I mean when we talk about it. But for a long time, people were like, "Is reinforcement learning a type of machine learning?" I'll die on this hill and say, yeah, it is. And we'll talk about what that actually means in a second. But for now, it's probably best for us first to talk about supervised learning. And the reason why we're starting with supervised learning is because it's probably the most easiest to understand, represent, and describe. Supervised learning is used for classification and regression problems. What this means is we're going to use this one data set a lot for our examples of supervised learning, because I want to show you classification problems over and over again, as well as regression problems. But one of the simplest classification data sets that is used in the industry is something called the iris data set. And this iris data set is it's a small data set of a couple of hundred flowers. And it's the dimensions of the petals and the sepals, the leaves of these flowers, three different types of flowers. And so we have, an array, a list of lists, and each embedded list has 4 values, and it's the petal lengths, widths, and sepal lengths, widths. And there is a supported or an additional object, which is going to be the supervised part of this algorithm, which contains the labels for each of those embedded arrays with 4 values, because it's one of 3 flowers where they're going to be labeled between 0, 1, and 2, but you could also just replace the number with the string, and that's what the flower actually is. So we use these supervised models for what we call classification and regression problems. So in the iris example, we're using it for classification. We have these dimensions, and we want to figure out what flower it is. Is it flower 1, A, B, or C? You can also use them for regression problems. So, just like our linear regression model, where we have an x and we want to, either find the slope of the curve or find the slope of a linear regression model or something, but we have a given x. We see how example data shows what the resulting y for that x is. It's similar to classification in the sense that you get a number at the end, but rather than it being a discrete category, it's like a continuous value. So supervised learning models can use discrete categories or continuous values, but what makes a supervised model supervised is that you actually know what the data corresponds to. So you have your 4 dimensions for your flower petal, but you also know what the flower is. It's supervised. You have the result. You have the what it should be as well, and that's important because that helps learning a lot, and it makes the model easier to check something on ground truth, and that's why it's used all the time for classification and regression problems, because it knows what it can, it has that ground truth to be able to compare to and say, oh, I think it's this, or I think it's this, I think it's 3, I think it's 2, or oh, I think the effect of these 4 values will have a resulting y of 27.3 or something. So common types of supervised models include support vector machines, random forests, and naive Bayes models. None of these make sense to you right now, I realize, but these 3 models are going to be covered in class alongside a couple of other supervised models. So I'm going to kind of leave it there in terms of describing what supervised learning is with words, and we're going to go into our syntax section and talk a little bit about how supervised learning might be represented in visually. So we'll draw something out. So see you in that section. Okay guys, how you doing? So here we are on our first syntax section for this course. We got a whiteboard here and I'm going to be drawing some stuff out for you. So we have our iris example. Let's just say we have some data, and this is going to be an like a data set with x and y. And we'll have some data points here. I'll tell you what the x and y actually mean in a second, but let's just say we have a bunch of data that looks like this. Okay, and each of these x's, if remember our iris data set, how we had petal lengths and widths and sepal lengths and widths, let's have this as width. And this other one as petal, or length. I'll just put L for now. I'll write length, I won't be lazy. Here is length. And this is going to be for petals. I'm just going to put length and width though. And the red X's represent one flower type or one petal type, and the red circles represent another. So with these machine learning models, what it can do is learn to find a way to like create a boundary and split this data set in half, or at least approximate it as well as it can. This would be like a very simple linear model. If we, let's build this out a little bit more and make it use like basically just use like a support vector machine example. So I'm gonna just kind of re-illustrate this really quickly. So we have our circles here, there we go. So we had that straight line before, remember? But let's just say our data looks something closer to this. Now this is like easy for us to build a boundary around simply because by eye we can see the pattern, but a machine can't necessarily see this. And we're also only using two features here, like the lengths and widths. Remember, this was width, this was length. So what happens if you have like 100 different features? You can't represent that in 2 dimensions. It'd have to be like 100-dimensional space or something, right? So what we do is we can build a machine learning model that, because this is supervised, it knows that this is a different class than this. The circles are a different class than the crosses. If this data was unsupervised, we wouldn't have the differences between these X's and circles. They would just look like dots. And I'll just put dots here like that. And we wouldn't be able to tell the difference. We would have to figure out like a different model in order to do that. And it would be basically a different problem. It wouldn't be able to do the same thing. But because we have the labels, we're able to build classification and regression lines around this kind of information. So in this case, this is easy for our naked eye, but this might not be necessarily easy for a machine. And also, like if we were doing a linear regression around this, where would be the most optimal line? If this is a circle, I mean, you can't optimize, because every time it strikes at the center is going to be just as like likely as any other one. So how would it pick? But because we have supervised labels, we know that these crosses are different than circles. Our machine learning models can learn to create boundaries around them, because what it'll do is it'll do things like, oh hey, I'll try a point right here. And is this point, more closely related to this x or this circle. If the point is much closer to the x, we can say, oh, okay, well, maybe with a cost function, we can say, that this would more likely be an x than a circle. And because of that, we can help draw our boundary to be a little bit more like circular around that part of the data. That is essentially what supervised learning models are trying to do. You know something about your data, so you have this data set. It's not just like a bunch of points and it doesn't really make sense. You don't know, is this a one flower from another? You know that there are different flowers, and you are able to make a distinction between them and like check yourself and check your responses to see if they're accurate in the first place. So this is the hallmark difference between a supervised model and an unsupervised model. In a supervised model, you know what the result or the outcome is supposed to be. In an unsupervised model, it's not that clear. You don't have that knowledge for whatever reason. So supervised models are a really good way to learn the basics of machine learning, and but usually you don't have targets, you don't have labels for your data because it's a complicated enough problem, and typically if there are labels for your data, that means that some person or you had to label them yourself, or you had some sort of additional analysis available to you in order to get those targets in the first place. So it doesn't tend to be the most intense machine learning algorithms out there, although they're really, really cool and they do some amazing things. And more just saying like they are not as difficult to understand and the math behind them isn't as tricky usually. But with that said, guys, why don't we do a recap on this class? So in this class, we learned about some basic definitions within machine learning. We learned about the 3 types of machine learning, and I spent a lot of time talking to you about what makes supervised learning different than unsupervised learning, as well as what features of unsupervised or supervised learning make it the way it is. So with that, guys, thank you very much and see you next class. Hello everyone, welcome to your next class. In this one, we are going to extend our knowledge on the types of machine learning models. We're going to spend a little bit of time talking about unsupervised and reinforcement learning. We're talking about these 2 models as opposed to just one at a time, because I spent a little bit of time kind of talking about unsupervised models as through a point of comparison with supervised models. So there's a little bit of information that we can add to this and pack in that will make this a bit more of a hearty lecture that will cover a couple of things at the same time. With that, in this class, you're going to learn how unsupervised models are working. I'm going to give kind of a very basic example. We're going to talk about what kind of tasks. We're also going to do this for reinforcement learning as well, guys. We're going to talk about what kind of tasks these types of models can accomplish, like what they're suited for, and then also talk about what they're commonly used for, like in the industry, like what kinds of models are being used that are considered unsupervised and reinforcement learning models. So with that, guys, we're going to spend a little bit of time talking about some key definitions within machine learning that are really important to address. They are both very important for all types of machine learning, but they're not specific to unsupervised or reinforcement learning. All machine learning algorithms have these features to them. So first off, all machine learning algorithms have to learn in some way. You have to teach them to find patterns in your data. And what we call teaching in our algorithms in machine learning is we train our data. So we have to give it lots of examples for it to train and learn from. Another term we use for training is fitting. So you'll actually see the term fit used in our code a lot, where we're building a model and we're trying to fit our data to a specific model. So it is a critical, important part. Every part of machine learning, or every algorithm with machine learning, requires that you have lots of data and that you pass that data through an algorithm that can learn from that information. And this is called training. So this is a very important concept to learn. The other important concept is the concept of testing. So after you have trained your model, you don't exactly know what it's learned yet. You have to actually try it out and see if it was able to find patterns of data that didn't exist there in the first place. And how we do that is by doing some testing, and basically we reserve some data that we haven't taught our algorithm on and see if it can predict things that we want it to predict. Or at least come out with a number that we hope is going to be close to what values similar to it are approximating as well. So sometimes we call this testing. We also use the terms predicting and scoring when we talk about testing in machine learning. And this is really just okay, your model has learned something and we got to make sure it learned what we expected it to learn. If it didn't do that, then we have to maybe go back to the drawing board and consider either some other model, consider sharpening our parameters, maybe we need better data, you name it. But testing is a critical component, because unless you know how accurate your model is, you probably don't want to be using it in the wild, because it won't do anything you want it to. A perfect example of talking about training and testing and why you need to do this is talking about image recognition. A famous real example of this is that some researchers tried to train a machine learning model to tell the difference between trees and cats. And they gave it all different types of training data, all these different trees and forests and all these different cats and different positions, and it was a supervised model, so this machine learning algo was able to try figure out whether it was right or not in the first place. But when we after we trained it, we tested it out and found that it wasn't very accurate at all, at least not from generalized images of cats and trees, because we found out that the images that we gave the machine learning algorithm, it was able to learn almost like a cheat or a trick that isn't something that we wanted it to learn. Essentially, we want this algorithm to try and learn a cat is different than a tree because, well, cats have eyes and whiskers and maybe fur and teeth that it can pick out from the image. What this algorithm was actually doing was looking at the corners of the image, where there is no information at all typically. And the reason for that is because pictures of trees usually have a lot of information in the corner because they're all very tall and the way that people take those pictures. So it was really just looking at, is there stuff in the corner or not? And if there's stuff in corner, that's a tree. If there's no stuff in corner, that's a cat. And that's not exactly what we wanted it to learn. We wanted it to learn from actual features and learn appropriately. So this concept of training and testing is really important, because you have to train your data or your machine learning on a lot of examples, and then you have to confirm whether or not it learned what you wanted it to learn, or if it figured out some sort of, chaotic, hard to find thing that no human would, or no reasonable analysis would lead you to believe, because it's finding some sort of bias or trick in the data. So with that, let's talk about the two other types of machine learning models here that we haven't discussed yet. So, unsupervised models are used for clustering and association problems. And the reason for that is we can't classify something that we don't know the classification for ahead of time. This type of model is designed for learning when you don't have any test labels. You have a bunch of features, but you don't know what the features correspond to. You have to oftentimes tell the algorithm how many, if it was doing something closer to a classification, you have to tell it how many classes exist in the first place. Now, with very chaotic data, that's not very common in unsupervised learning. You don't usually know how many clusters you should be expecting. But in order for these to work, you have to kind of give it something to work with. You say, okay, I expect a certain amount of associations or a certain amount of clumps of data that we would try and create this association solution to. So, let's say you have our different flower types, and the dimensions of those flowers are clumped together in very specific areas. Your machine learning algorithm will be able to find where those clumps are, where the associations exist, but they might not be able to tell you how many associations it's supposed to find, because it doesn't know, it doesn't have that context. So common types of unsupervised machine learning models include k-means clustering algorithms as well as hidden Markov models. I'm going to basically describe what a k-means clustering algo is doing in the syntax section of this course. But before that, I kind of want to just really highlight what reinforcement models are, and then we can draw some stuff out and explain everything as it's going from there. So first, reinforcement learning has kind of become its own type of machine learning model. It was a little bit debated for a while. I still think it's a machine. I still think it's its own type. But how reinforcement learning works is it's almost like a hybrid in that you don't have labels for your data, so it's unsupervised in that sense. But you almost you create a scoring metric, or you find a way to encourage certain behavior within your machine learning model. You can think of it like running a race, or looking through a maze, or trying to navigate through a maze where there are a certain amount of feet from the exit, and you can score how close they are to the exit, or how close the machine learning model is to the exit, and it can learn through that scoring process. That's kind of why reinforcement models are considered hybrids, because labels don't exist, but you can encourage label-like behavior by giving it little rules that it can learn from. So common types of reinforcement learning models use something called Monte Carlo methods. That's not exactly a machine learning model itself, but Monte Carlo evolutionary algorithms are considered reinforcement learning, where you kind of consider that if you consider each iteration or each time is trying to learn something as a different genus and species, you can give it a fitness score, and that score is the reinforcement part. So let's go into an illustrative example of what unsupervised and reinforcement models are doing and how they look, and then we'll move into deep learning in our next class. So, okay, let us start with unsupervised models. So I'm going to create a little graph here, and unlike remember our supervised models had circles and crosses, right? So I'm not actually going to be making circles and crosses. I'm making just one type of data. We don't know one class from another. All we know is that one cluster here is there appears to be two clumps. There are two sets of associations when we look at this graph by eye. That is not what you would absolutely be able to do if you had more data and very complex or stochastic information, where you have multiple, dozens of different or hundreds of different features to look at, and this graph starts to become very complex in terms of dimensional space. If we just add a third dimension here and had 3 features, things would start to get a lot more hairy as well. So we're just going to start with 2 here, and I'm going to explain how an unsupervised model might work. So I'm going to talk specifically about k-means clustering algorithms. Remember that I said that unsupervised models, typically you need to tell them how many different associations it should be expected to learn or look for, and how it will start to build its associations is it has this data here, and a k-means clustering algorithm, what it'll do is it'll select a point at random, just boom, right here, this red dot, and say, okay, I have this point here. How far is this point from all of the other data that exists here? So we have this point here and this point here, and you can basically use geometry to calculate how far away this red dot is from all of these data points, as well as from the data over here. And because it's looking for associations for basically 2 groups, it can find that the top half of your data that has the lowest Euclidean distance, and say, okay, because this group is so far away and this group is really close, I'm looking for one cluster at the moment. We're looking for 2, but in this example, I picked one arbitrary point, and I want this arbitrary point to be a centroid that can associate one cluster from another. So this cluster is much closer, the bottom cluster is much closer to our arbitrary point than the top left cluster. So because we had this knowledge and this learning after training or after calculating all these distance metrics, what we can then do is this centroid in the next iteration can move closer to this clump and become even shorter distance over time, and it can learn by just quickly pushing or nudging over and over again iteratively into the center. And consequently, it would also do this in the other direction all the way up to this cluster because we were looking for 2. But basically, that is how an unsupervised model is working. It's trying to find clusters, associations, clumps of data that stick together and build boundaries around them, saying, okay, this clump is different than this clump because they're very easily segregated using like a k-means clustering algorithm. Okay, so let us say we have a reinforcement learning algorithm and we're running a maze. So here's a little makeshift maze I'm making. It's going to start from the bottom here. We're going to have like a little bit of a veer off, like a dead end, and it comes up all the way to the right. One more dead end, and then we have our exit here. And so how we can score this, how we can build this is essentially saying like, okay, we can score this whole thing by saying the distance between the distance that the machine learning algorithm is from the exit according to some steps. And let's say that, you know, if we were, all of these little lines I'm making are like steps that the algorithm will take to, that it can take, rather than doing like feet or some sort of crazy distance metric. So let's say if we were to like segregate all of these into different steps, like a board game, that in total, the distance between the entrance and exit is something like, it's a little bit less than this, but I'm going to say 20 for ease. So 20 when we start at the very beginning. And we can tell our machine learning algorithm that it needs to get as close to 0 as possible. So how this reinforcement model will work is it'll start to make decisions. It can only go forward. So in this iteration, it'll go forward and it gets closer to the exit. It brings it to 19. And most machine learning algorithms start with one step at a time, and then they actually stop altogether. So it went forward and said, okay, I did my first iteration, got a little bit closer, let's start from the beginning now. And so for the next iteration, it'll go forward, and then forward again, and suddenly it's even closer. And then it'll stop. It'll go, okay, so something even better happened. That's great. Good knowledge. And in the next iteration, it'll continue to go. And we get to the middle here, but at some point, it has to make a decision between choosing left or right. And let's say in our example, it moves to the right. So eventually this got down to 617, and then from moving right, it went back up to 18. So this reinforcement learning algorithm now says, oh, I've just been punished. I actually did something wrong. Like I have been penalized for this choice. So knowing that I went forward, and I was getting smaller, and then I finally had a choice between going left or right. When I picked right, my score went up. Maybe on my next iteration, I should go left instead. And so now rather than it being 18, it's going to be 16. And it can learn how to behave in very complex ways by giving it nuanced scoring. And you can start to see how this is not exactly supervised, because you're not saying, oh, well, you're getting, you know, it's a classification, so you can't like really get it to say, oh, this is blue and not green, or you know, some sort of state. You're getting it to try and perform and do a behavior that doesn't really have labels that can work. So you're kind of artificially creating labels and building a bit of a hybrid between an unsupervised and supervised system, where you're kind of slowly dragging the score in a way to get it as close to an optimized value as possible, even though it doesn't exactly know what it's doing, or doesn't even know really how to check itself if it's accurate or not. Okay, guys, that is, I think, a sufficient description of what's going on with reinforcement versus unsupervised models. So in this class, what did we learn? We did an explanation of unsupervised learning. We talked about how a k-means clustering algorithm will try and find clumps of data and slowly and iteratively move its center point to create boundaries that are within the middle of a clump of data. We learned that unsupervised learning is really involved in doing association and clustering problems. We talked about a basic description of reinforcement learning and how it is a hybrid model using both kind of supervised methods and unsupervised methods. And then we talked about two very, very important concepts within data science, which is training and testing. The example I gave you of both the centroids moving towards the center of clumps and the machine learning model, the reinforcement learning model trying to get to the end of the maze, are all examples of training. if we were then to confirm or test, okay, we give it some new data or try it on a different time or a different maze, that test data would be, what we throw at it to see if it was right or not. That, guys, thank you very much. In our next class, we're going to talk about deep learning a little bit and basically leave our deep learning at that point because it's too complicated to talk about within the scope of this class, but I will explain basically what's going on with it. So thank you very much and see you next class. Hello everyone, welcome to your last class for this section. In this one, we are going to briefly talk about deep learning, as well as talk about a couple of high-level concepts within data science as well. So you're going to have a basic example and representation of deep learning. We're not going to spend too much time with it within the confines of this course because it's something that probably needs a lot more time and attention than just like an hour or two can give it. But with that, I still think it's useful to understand the basic process of what's going on with deep learning because it's becoming more and more important within data science and machine learning. So I figure let's just have a description of it so you can know the differences between machine learning and deep learning and talk about it in intelligent ways with people. So in this class, we are going to talk about how deep learning models basically work. I am then going to introduce to you the a high-level concept. I call it the data science workflow. It's kind of like these 5 stages of any data science work that you should be considering when you are doing kind of data science analysis, and they are required at every step, basically no matter what you're doing. What is deep learning? This is kind of our definition section, but I need to spend a little bit of extra time on it. I kind of said before that deep learning is a type of machine learning, but rather than it doing the kinds of problems we've talked about with supervised, unsupervised, and reinforcement learning, where you have training data and test data, and it's kind of modeling or trying to learn using kind of like processes or steps that are kind of like in a manual where it's starting to slowly creep towards a cluster, or you're starting to create boundary spaces around targets. What deep learning is trying to do is it's trying to tackle similar problems, but it's modeling its learning in a completely different way. It's using kind of a very high level representation of how neurons work in the brain. And we're creating almost like a very, very stupid brain. Remember that your human brain has got billions and billions of neurons, and they are all interconnected. So you start to look at like the synaptic connectivity of a billion by a billion neurons, and it starts to become extremely complex network. Our deep learning networks, don't get beyond like tens or maybe even hundreds of thousands of neurons with like the most extreme computation available. So we really have like very simplified representations of brains, and like how we are building these things doesn't even really encapsulate effectively or completely the nuance of how a neuron is working and learning and adjusting over time. It's approximating it using kind of like almost like high level heuristic representations of these concepts, but it doesn't it doesn't even come close to how real brains are working, guys. So when we talk about deep learning, it's a very exciting area of machine learning at the moment, but most people get a lot more scared of deep learning and artificial intelligence than they really need to be, because we're nowhere near as sophisticated as our own brains are. So deep learning models are really good for unsupervised problems that are extremely stochastic, that have a huge amount of variance, and it's not very clear how to like build an association problem out of it. It needs to be a blend of everything. So deep learning models are like they can be very smart and do very unexpected things, but they appear to be a lot more dynamic in terms of how they can learn and the things that they're learning. In order to build a neural network, a deep learning model, there are 3 things that are required. You have to have an input layer. So this is like a layer of neurons that would be activating to stimuli. Let's say, if you guys don't know how your eyes work in the brain, basically you have these receptors at the back of your eye, and it sends a bunch of information to your occipital lobe, which is at the back of your head, and there's this whole sheet of neurons that fire very selectively to very specific types of stimuli, like the angle of something you're looking at, or the color, or the shape, and that activation in the brain is the closest proximal metaphor to that would be this input layer, where it says, okay, I have activated this set of neurons. You then have like a hidden layer, which are neurons that are connected to that activation layer, that are doing processing, and they're all doing different types of activation depending on what neurons are activating and what strengths. And you can have multiple hidden layers that are doing all of these complicated interactions. Lastly, you have an output layer, which is kind of like your final neuron that activates, saying, okay, well, I think this is situation A or classification B, or so on and so forth. So it's almost like the final neuron that codifies what the next process should be. So I will illustrate what these different layers actually look like with our whiteboard, but these are the terminologies that we need in order to understand this in the first place. So with that, let's move into our syntax section and talk about this a little more. Okay, let us do a simple example of how a neural network or deep learning is going on. So I'm going to create a input layer that is comprised of 4 neurons, okay? So I'm going to represent neurons as circles. 1, 2, 3, 4. And let's just say that these neurons actually represent a pixel on an image. We have a very simple 4-pixel image, and we can activate, and it's only like in grayscale or black and white. So when a neuron activates, that means it's white, and when it's unactivated, it means it's black. So let's just say we have 2 neurons in our input layer that are activated. We then usually have a set of hidden layers where we have, maybe 3 neurons. Now these neurons don't correspond to to the stimuli itself, but every neuron in the input layer is typically connected to every neuron in the hidden layer. So the interactions that are going on between each of these neurons gets passed on into this next layer that has a reduced layer size and has a reduced kind of activation process. Now notice one important concept here is that the sum of all of these activations, like the connection strengths for all of these neurons, should sum to 1 or like 100%. You can't have more than 100% activation. And so the interactions between how strong this top connection is with this hidden layer neuron compared to this third neuron to the first neuron in the hidden layer, let's say that this one is a lot weaker, the interaction between this neuron, between the top neuron activating and the third neuron not activating, will create a kind of response in this hidden layer neuron that would maybe, let's say, be like 0.7 out of 1. Where for this connection specifically, you can then maybe it's 0.2 overall and 0.1. You can then have additional layers. Usually we have multiple layers of hidden layers that are doing different connections or are connected in different ways, and this is what gets these models very complicated and very dynamic, is that the interactions within the hidden layers are so complex that it can create these very complicated states that it's able to do many different things from. And so lastly, so let's just cut this off here like that. That's our hidden layer. And then finally, for our output layer, we're trying to determine between like cats and trees, like our previous example. If we're really trying to figure out between 2 or 3, let's just do 3 types of classification: cats, dogs, and birds. And so your output layer, if this first activation we have here was a bird, might get, after all of these connections are activated and like respond and do this really interesting interconnected process, after these are all connected and you get a activation strength or an activation output in this final layer, let's say that 0.8 here, and then 0.1, 0.1. So we could, if this was activated with a strength of 0.8, this neuron or this output layer is saying it's probably whatever this classification is probably this state, and it's basically just saying that okay, it learned that it's class 3 as opposed to class 2 or class 1, so it's like a bird as opposed to a dog or a cat. That is the fundamentals of how a neural network is working. Now expand your hidden layer size, expand how these neurons are activating, expand how many layers there are, and run wild with this. And this is where this area of deep learning starts to become extremely specialized and difficult, because the amount of computation and the subtlety of how you are building these interactions and networks is so complicated and can change based on very subtle differences. It requires a lot of specialized knowledge. But understanding the basics of how a neural network is operating is probably going to be very useful for you guys, so you can have these conversations and learn about it deeper in the process. That is basically how a neural network works. So I want to talk about one last thing, guys. I want to talk about this data science workflow that I mentioned at the beginning of class. There are basically 5 big portions of data science that when you're building machine learning algorithms, you have to consider that if you don't, you'll end up having basically a bad time. And these are really important steps that I kind of follow every day when I'm building my own machine learning algorithms. So first is you have to kind of look at the problem that you have and determine what model to use. No one's going to say, oh, this is a supervised model, and the best one, because everyone else has done this before, is going to be using a support vector machine. You don't have that benefit when you're a data scientist, because you're the expert and you're the one who has to determine it. So it's really important to spend a lot of time looking at your data, looking at the problem, and figuring out what the best method should be that exists or you realize for trying to evaluate this problem. It's going to save you a ton of time. The next thing that a lot of data science must do, is processing. A common axiom within data science is that 90% of your work is really just getting your data into a shape that is appropriate to build that is designed for your machine learning models to learn on. Most of the work is getting it into that form, because data is really chaotic and messy, and people don't really think about how to organize things until after they have a problem they want to solve, rather than being proactive about it. So we spend a lot of time accessing data, scraping data, massaging data, and forming it into a version that we can then do real analysis on. Another important factor to consider are parameters, meaning you have your model, but it's going to be really important to learn for your model to have the most sensitive parameters possible for your problem. And the reality is, parameter tuning, figuring out how important each parameter should be, or what values you should incorporate into them, no one knows how to do it. And it's not because we don't know what we're doing, it's because it's not abundantly clear how, what parameters to tune for a given problem. It's really kind of a trial and error process, but it does take up a lot of time. Determining what cost function you want to use for your model as well is an important one. There are so many different distance metrics out there that you might want to use a different one, or it's more appropriate to use one over another. So thinking about how am I parameterizing my model is a really important question that needs to be thought of and considered. Lastly, the last 2, we talked a lot about them in last class, so I won't spend lots of time on them, but training and testing. So the next thing, once you have all those things in line, is building your training data, making sure that you select a training method that is adequate, that is comprehensive and robust, that isn't going to cause problems for your machine learning model. Maybe it will not learn anything, maybe it will learn the wrong thing. So training is an important aspect of making sure that your machine learning model isn't cheating or kind of learning something you don't expect it to learn. And lastly, and possibly most importantly for at least the people at the other end of this work, is determining how accurate or how good your model is after training. If you want to be able to have the best, most accurate model possible, because people want, for whatever task they're doing, for the machine learning to be as perfect as it can be. So we have built kind of these complicated methods of testing the accuracy of our models, and learning how to do that will be a part of this class. So we're going to do all of this stuff. We are basically going to start with the bottom three first, and then open up over time. We're going to start with parameters, then training, then testing, then processing, then hypothesis. I know that sounds counterintuitive, but I promise it's probably the best way to learn without, going overboard. It's kind of weaning you into these things one step at a time, so that once you get to that point, it becomes a lot easier. So do trust me, we will get to all of these as part of our data science workflow, but we're going to start from smaller beginnings and work our way up to it. Okay, guys, this was great. Thank you very much. You've now been introduced to how deep learning works. I told you a little bit about this data science framework. You're going to see that image again and again, because I'm going to be talking about different components and aspects of it. And you learned a little bit about how these frameworks work for both supervised, unsupervised, and deep learning methods. So with that, thank you very much, and see you next chapter.